maybe I don't think I'm going to get to the end of everything. So I might just keep recording videos on Monday, Wednesday, Friday until it's done. That way you guys have access to them to study if you guys need them. Of course, you guys are still welcome to attend, but it's optional, of course. Any comments or questions on things that we've been doing? Yeah, Jeremy?
Sorry. So you mean that you're going to continue, so like next week past the end of the semester is what you mean?
Yeah, I'm just gonna continue so that you guys have a resource.
Is it going to be at the same time or?
Same exact thing. I'm just gonna just continue. Yeah.
All right, great. Yeah. Thank you.
Yeah. Any comments or questions or anything? Okay, so let me kind of remind you where we were, right? So we were talking about splitting of exact sequences, right? And so there's kind of a couple ways that we could define splitting, right? You could have a left splitting, or you could have a right splitting, and or you could have that it's a direct sum, right? And so a left splitting means that you have a module map from M to M prime. And then a right splitting, you have a module map from M prime prime to M, right? And it's once you go back and then go forward through P, it's the identity on M. Or you could go forward and then go back via the splitting in the first case, right? And then you'll get you'll get the identity on M prime. So that's what a module splitting is. And then those are being left split and being right split were equivalent to having your module being a direct sum, right? Not only that is that you have this other condition that we talked about at the very end. Let me see if we have it. But it's not just that it's a direct sum, but that the maps that go along in the exact sequence are the maps that you would want them to be, right? Meaning that they're the inclusion and then the projection. Okay, and now I'm going to use this to give a criteria today, or give a characterization of projective modules. As direct summands. Of free modules. So before we proved that free modules were projective, right? And the trick to that proof was that so the trick to the proof there was kind of like to use the basis elements, right? And so you can lift maps from a free module, right, by just picking where the basis elements go. So if you have a surjective map, right, and you have a map from your projective module or from your free module into the target of that surjective map, right, then well, what you do is you take the basis elements, right, you see where they go, and then since the map is surjective, you can pick some inverse images, and that allows you to kind of complete a diagram where you can lift so what we call this a lift, where we lift the map into the target to the source. Okay, it's not a unique lift, but that thing exists, and that shows that projective modules are free because that's what it means to be a projective module, that you can lift from these surjective maps. Okay, so what I'm going to prove now is the following. So I'll prove the following theorem, and I'm going to use the splitting criteria for this. So let M, or let's say let P be a finitely generated R module. Okay, and what I'm going to prove is that P is projective. Excuse me. So P is projective if and only if there exists some free module free module F, where F is isomorphic to P direct sum P prime. Okay, and this thing says that. So let me just box this up for us. This part says that P is a direct summand of F. Okay, so a direct summand is that you can write something as a direct sum of multiple things, and a summand is one of the pieces of the sum. Okay. All right. So let me give the proof. Okay. So what we're going to do is we're going to let so since P is finitely generated. Oh man, why does it keep doing this? Since P is finitely generated, right? There exists a surjective map. Surjective. There exists a presentation, right? So a surjective R module map, right, from a free module here, F, which is okay. So I'm going to write it like this. But you could have I be a finite index set. So in our case, this is like R to the n, okay, into P. Okay, so that's what it means to be finitely generated. So you could actually replace this condition here in the theorem with finitely generated by having one of these maps from a free module, right? Okay, so it needs to be generated, like maybe, this is indexed by I generated, right? Okay, so all right, so since P is projective, okay, so now we're going to suppose that P is projective. So this is what the finitely generated hypothesis is. Okay, so we're going to do the first part of the proof where we suppose that P is projective. Okay, so since the map F is surjective, then the map F star here. So what we're going to do is we're going to take maps from F to P. So I'm just going to apply our functor represented by P. So let's see. This is not quite right. FP. So here I need this to be surjective. So I actually, let's see. So this is not the right way this goes. So I had it written down the wrong way here. So I want to see that this is if I have that this is surjective, then I'm done. But I don't have that this is surjective automatically because this isn't applying so let's see if we can do this another way. So let's just apply P to this thing. Let's see if we can do this. So do you guys see what I was doing? I wanted this thing to be surjective, but and now I'm realizing in my notes this isn't quite right because what we do have is we have that. So this is not what we have. Okay, this is applying. Let me just show you what's going on. This is applying mod R dash P to the above map. So we want to apply mod R P blank. Okay, so so let's do this. let's get rid of this. Let's see what happens if we do this. And then if I get stuck, I'm just going to move on to another topic. Okay.
You apply mod r dash I for injective modules, right?
Yeah, exactly. That's the one. That's the one that is exact. So yeah, the other one is for inject. Exactly. That's the way that you do it for injective modules. So for injective modules take surjections to injections is free, but injections to surjections is not free. Yeah. So for injective modules, when you do the co-represented one, which means dash the second thing, right? Then that takes, it's injective if it takes injections to surjections. Surjections to injections is always free in that case. Okay, so let's do this. Let's try and fix this and let's see if this works. If it doesn't work, I will come back to you tomorrow with a different thing, and then we'll just move on to tensor products. Okay, so let's just see what happens. So we have this map here, okay? And so let's do mod P, or P, F, to, oh, this looks reasonable. Mod R, PP. Okay, this looks right. Do you guys agree? So this is F lower star. Okay, so this is, so this thing here is this thing applied to the map F. Okay, and so this is F lower star. So so by projectivity of M, or projectivity of F, this is also surjective. Agreed? Okay. So now what we can do is since this is a surjective map, yeah.
What do you mean by projectivity of F?
Oh, sorry, P.
Okay, okay.
Almost every time when you say something, I'm just like, I know I did something. Yeah, good catch. Yeah, projectivity of P. Okay, so by projectivity of P, this is surjective. Agreed, Liam?
Yes.
Okay, cool. All right. So what we're gonna do is, okay, so this is like the kind of like a Yoneda-ish trick. What I'm gonna do is, well, I'm gonna take the identity here, in here. So this thing contains the identity. And then I'm gonna lift it. Okay, so there exists some, okay, so this is gonna be a splitting sigma PF such that we have that F star of sigma is the identity on P. Okay, and let's just kind of like write out what this is. Okay, so this is F composed with sigma is the identity on P. All right, and so now let's kind of just like write out this exact sequence here. Let's just kind of write out the diagram here. So we have a map from P to, so we have a map from P to F. Let's write this out. Okay, so we have a map from P to F. That's what we called, that was our original map F. So this, oh, sorry, F to P. We had F, it surjects onto P. Okay, and then we actually have an exact sequence. So this is F, this is the kernel of F, right? And so we have an exact sequence like this. Okay, and then what we were given was, so this little doodad here, right? So this goes from P here back to this. This is sigma, and it has the condition that when I go sigma and then I do F, that's identity on P. So this is a section. So this is a section. Okay. And so this proves that this proves that that F is a direct sum of P and some other thing, P prime. Well, we know what the other thing is. It's the kernel of F. Okay, so that proves one direction. Oh, so we fixed it. Okay, so yeah, so the trick is to apply the functor to the presentation. Okay, and that gives us a section. Okay. So conversely, so for the proof of the converse, for the proof of the converse, we will need a little more. We'll need some facts. Okay, so I'm going to give you like a little exercise here. So exercise is this. Is that so if A, B, and C are R modules, right? And then I want you to check that that just direct sums. So this is isomorphic too. And then we also have that. Okay, A, B direct sum C. A, okay, AC. Okay, let me also just say, okay, so and that these maps, these isomorphisms are functorial. And I think you guys are at a stage now where you maybe know it. Well, I'm going to talk about this again when we talked about tensor products. But Dumb and Infoot, I think they'll omit that this important part, that these maps are functorial. And what does that mean? So that means that they behave well, right? They behave as expected with respect to maps. You know, A to A prime, B to B prime, and C to C prime. So like you could try and, so let me just put this here. You could do the exact same isomorphisms with A prime, B prime, and C prime, right? And then you could have maps from A to A prime and B to B prime, and then you have maps from the different Hom things, and you'd write out a big, huge diagram, okay? And so the statement that I'm making is that the diagram that you would get, the obvious diagram that you would get from just kind of like tracing through what these maps would do and how the functor is contravariant or covariant, right? Well, that diagram commutes, okay? And so that's important in applications. It's kind of the same sort of thing that I was saying, that not only do you have a direct sum, but that the direct sum is when we had that splitting, right? That the two maps from that direct sum are the two maps that you want. It's the same sort of idea, that you kind of have to check the way things behave with respect to maps as well sometimes. Okay, so it's not just enough that you have this isomorphism here, but you also need to know that this isomorphism here behaves well with respect to morphisms of modules. Okay, the only reason I'm bringing this up too is because I need this property in showing that that free modules are that direct summands of free modules are projective. Okay. I guess there's another exercise that I need to tell you. So yeah, so I think the good exercise here again is to write out, so to write these isomorphisms out, and then write out what it would mean for these things to behave well with respect to morphisms. Okay, so the other exercise that I want is that if, okay, so if Fi is a map from, let's say, Mi to Ni, for I is equal to 1, 2, then the map here, F1, F2, from M1 direct sum M2 to N1 direct sum N2, this is surjective. If and only if F1 from M1 to N1 is surjective, and F2 from M2 to N2 is surjective. Okay, so this is the other exercise that I'm going to use. Okay, so that if you have, when you're doing like two things in parallel, right? You have an isomorphism if in each of the direct summands it's an isomorphism. It's a surjection. If it's a surjection in each of this, maybe I should do this surjective, and then I could say injective and bijective as well. So you can check these properties, summand by summand. Okay, and that's what I'm going to do. Any questions on these two exercises, or why I'm bringing them up? Okay, so let's go back to what I was doing. That was showing the converse. Okay, so we're going to suppose that now that P is a direct summand, and we're going to prove that it's projective. Okay, so suppose now, so suppose now that F is isomorphic to P direct sum P prime. Okay, so we will show that P is projective. Okay. All right. So what we do is we'll okay. So what we do is we let let V to V prime prime be a surjective morphism of R modules. Okay, so we have here, so now we're going to apply F. So by since F is free, F is free, it is projective, and maybe we should give this a name. Let's call this G. Okay, and the map here. Here we're just going to write down what this is: mod R F V. This is G star mod R F V prime prime. This thing is surjective. So this is surjective, and this is surjective. Okay, and so now I'm just going to break this down. Okay, so on one hand, I'm just going to use that this thing here. Okay, so this thing here is, this side here is isomorphic to, well, this is mod R, then we have P, V prime prime, direct sum, mod R, P prime, or sorry, this is a V just here. PV like this, and the same thing over here. And so we have mod R PV prime prime, direct sum mod R, P prime V prime prime. Okay, so we have that it's a direct summand. Okay, and so so this is made up of two maps now. So now we have to use the kind of the functorality of this thing. So we get that this is made up of two maps, right? So this map from here to here is made up of two maps. Okay, and by the exercise, both alpha and beta must be surjective. So that implies that since we started with an arbitrary map here, right, from V to V prime prime, where is it here? We started with an arbitrary surjection, so that's like our test map, right? This implies that both P and P prime are projective. Okay. And that's it. That's all there is to this one. Any questions about that? Okay. So so now I'm going to move on to oh, okay. So there's a little bit more that we could do. So there's a kind of like a similar discussion for injectivity. So let me just kind of do some